Here we are, section 5.7, and check out the title of this section, Apply the Fundamental Theorem of Algebra. I don't think you can get any bigger than Fundamental Theorem of Algebra. So, and we've actually been talking about it, quite a bit in this chapter already. So what happens, first we do want to identify this little key vocab word, which is repeated solutions. So for every function, when we set it equal to 0, k is a repeated solution if and only if the factor the factor x minus k has a degree greater than 1 when f is factored completely. So here's an example. Again, for me, the other day in class, I would have said, hey, the answers here, if I set the function equal to 0 and solve, the answers I was writing on the board would have been 2, comma 2, and I wrote it twice because it was, the factor represented twice, comma negative 1. So again, if you call this a repeated solution and think of them as two possible answers, then the fundamental theorem of algebra will work out better. So here is the fundamental theorem. Basically, it says a polynomial to the nth degree, and n is greater than 0, then the equation, when the equation set equal to 0, has at least one solution in the set of complex numbers. And even further, right, if you have a polynomial of n degree with exactly n solutions, provided that each solution repeated twice is counted as 2 solutions. Each solution repeated 3 times is counted as 3 solutions. Very wordy. What are we getting to? The fundamental theorem of algebra basically tells us if I have a third-order polynomial, I have 3 solutions, 3 complex number solutions. So you could have imaginary solutions. They count. Again, x to the power 3 will have 3 solutions, and we had to keep kind of harping on, hey, if you have a repeated solution, we consider it twice. So you have if you have some polynomial that's to the power 5, there are 5 complex solutions. And again, you may look at 0 and say, oh, that's one solution, but in this case, it's a repeated solution. And there you have it, the fundamental theorem of algebra. So let's do example 1. Find the number of solutions. Again, this isn't hard, but it's a big deal, right? It's the fundamental theorem of algebra. Find the number of solutions or zeros. Again, same thing, and I actually have used x-intercepts or roots as well. For each equation or function. So here we go. This first equation, how many answers are there? Well, this is a degree 3 polynomial, so we should get 3 solutions. And here, this is a function. We set this equal to 0 and solve. This is a 4th order polynomial, degree 4, and we should get 4 zeros. So very, basic, but conceptually, it's a big deal. Fundamental theorem of algebra. Here we go. Hey, try this one. This is your first check-in. So here's your function. Can you state the number of zeros of this function? I'm not even going to tell you hit pause because I'm sure you already know the answer. And there it is, 3 zeros. Nice check-in. So we have these two. These are a big deal. Basically, it's a complex conjugates theorem. So if you have a polynomial function with real coefficients, and you find that, some complex number, let's make up a number, sometimes easier. Let's say 2 plus 4i is one of the solutions. Then by the complex conjugate theorem, it's that there's another solution that is the conjugate. Does that make sense? So again, anytime if somebody says, hey, I've got one of my zeros is a complex number, with an imaginary part, you can say right away the other one. So let me give you another example. Let's say I had 1 minus I. Then I know that the other complex answer would be, and hopefully you're saying 1 plus I. Let's make this a little simpler too. Let's say somebody comes up and says, hey, check it out, I got an answer. It's negative 5i, but I'm sick and tired of doing this problem. I don't want to solve for the other one. You'd say, oh, no problem. The other answer would be 5i or plus 5i. Again, complex numbers come in conjugate pairs. That also is true for irrational conjugates. And so in this sense, let me just skip right to it. Let's say we had an answer of 2 plus the square root of 3. You know that there's a second answer to that function that would be 2 minus the square root of 3. And the key word here is conjugate. So I use this word a lot. I'm not sure you're as comfortable with it. But again, it's a powerful world in the algebra sense. So here, let's apply it right now. So example 3, write a polynomial function of the least degree, meaning you wouldn't want to blow it up even bigger than just the possible answers that are given, that has real coefficients and the leading coefficient of 1. The solutions, they tell you, hey, one of the zeros is -2, and they also tell you that you have a 0 of I. And again, from the complex conjugate root, you know that there must be a second answer that's -I. And so finally, if I wanted to figure out that equation in standard form, I would first plug in the answers. So I'd get x plus 2. And hopefully you're looking at this going, oh, of course it's x plus 2, because if I set this equal to 0 and solve, I would get an answer of -2. So be careful how you do the signage. Here I'd take the next answer of I and write it in as a factor, and then take the last answer. And I should write minus -I, but we know that two negatives just go to positive, and we have those answers. So that's our factored form. I'm going to multiply this out to go into standard form. So let me take the first factor and just hold it for a second. Let me multiply this second piece, and you should see that I'll get x squared. The middle term is what's interesting, right? I'm going to get plus ix and then minus ix, and that's huge, right? And that's what the conjugate does. It cancels out this middle term, and I'm left with I squared at the end. So right away, these guys we can just say cancel, and then I squared. Do you remember what the rule for I squared is? Of course you do. I squared is equal to -1. So this ends up going to +1. So let's rewrite this in simplified form. This is x plus 2, parentheses, and then parentheses, x squared plus 1. Again, hopefully just take a look at this. Look at this factor, the way it's written. If I set this equal to 0 and solve, wouldn't I get the answers -I and +I? So again, I'm feeling like I'm doing this, I'm on the right track. I'm going to multiply one more time. I get x to the power 3, and I love this 3, right? Because I started, I had 3, well, they only gave me 2 answers. That was kind of, annoying, but I knew right away if I have I as an answer that its complex conjugate would be -I. So I started with 3 roots, and my final answer is going to be a power 3. But let me keep going here. Then I'm going to get plus 2x squared, finally plus x plus 2. And that is your function, right? This is your final answer. F of x, this third order polynomial, if you went backwards and factored it out, would give you the 3 answers, -2, I, and -I. All right, why don't you go ahead and try. So you're given two zeros here, 4 and -2i. And we would like you to write the equation for this polynomial. So again, hopefully you understand that there is another 0, and I'm not going to give it away, but hopefully you do know what it is. So hit pause. Why don't you go ahead and write it in factored form and then expand out and get your final answer. When you're ready, hit play. And here we go. So you hopefully did realize 2i was also an answer. Then you would write it into factored form. Again, be very careful. This is x minus 4 to get a +4 solution. Again, these guys don't matter because if you mess this up, well, it'll be okay. If you expand or multiply the last 2 factors, you should see that the middle terms cancel, and you may not even write these anymore. I just thought I'd show you. I squared again is -1, so this goes to +4. And again, maybe a little reality check. Hey, if I set x squared plus 4 equal to 0 and solved, I would get x squared equal to -4, and I would get these 2 roots. So that feels great. And final expansion. Hey, well done. I will see you tomorrow in class.